Brad received his PhD in civil engineering from Caltech. Afterwards, he first joined the USGS as a Mendenhall postdoctoral scholar and now is currently a research geophysicist there in the Earthquakes Hazard Program, where he has contributed to the development of the San Francisco Bay region 3D geologic and seismic velocity models, as well as strong ground motion modeling of the region. Many of you may know him as part of that trio, Aagaard, Williams, and Nepley, who are the lead developers of the finite element code PyLith. We are fortunate today to have Brad here to give us an overview of PyLith, plus a preview of the multiphysics and other features coming soon in PyLith version 3.0. So Brad, take it away.
Okay, thanks everyone for showing up today. And so first I'd like to give sort of a very general view of PyLith, and I'll discuss some of the features in the current release, and then also look forward to what we're working on for PyLith 3.0. PyLith is a modern community-driven code for crustal deformation modeling. As Lorraine mentioned, the developers are myself, Matthew Nepley, who is now at Rice University, and Charles Williams at GNS Science in New Zealand. And when we started this project about 10 years ago, our goal was to combine the dynamic modeling capabilities available in a code that I wrote called EQSIM with the quasi-static modeling capabilities of Tecton that Charles Williams developed. And Matt Nepley has provided sort of a computational science background to really up our game and help us use modern software engineering to develop an open source community code. It is very modular in design, has extensive testing, documentation, and easily distribution and installation on a variety of different computers. PyLith version 1.0 was released in 2007. And we've had a number of releases since then, and the map on the lower right shows the downloads that have happened over the last year. So you can see we have a number of users in the US, Europe, Asia, and then a sprinkling of users in South America, as well as some in the Southern Pacific. Some of the applications that PyLith is well suited for are generally classes of problems related to elasticity where the geometry does not change significantly. So if you're looking for a code that does things like formation of faults and mountain building, that's really not the realm of where PyLith focuses. That's sort of more the long-term tectonics regime within CIG, where formerly the code was Gale and now Aspect has become more prominent. PyLith is much more suited for sort of quasi-static modeling associated with earthquakes on the scale of, say, up to about a few earthquake cycles, as well as interseismic deformation. And so some of the research questions that are being associated with PyLith are looking at strain accumulation associated with interseismic deformation. Someone may want to know what the stressing rate is on faults, say X and Y, given some background deformation of plate tectonics. They may want to look at where is the strain accumulating in the crust. There's also sort of looking at coseismic stress changes and fault slip. So given the deformation from an earthquake, one can examine what the slip distribution in an earthquake might have been. PyLith has some capabilities for generating static Green's functions in complex 3D structure. Also, imposing slip in an earthquake and looking on the stress changes on complicated surrounding faults, as well as modeling the post-seismic relaxation in the crust. So examining various viscoelastic rheologies and their spatial variation, as well as looking at aseismic creep or after slip on the fault and looking at the trade-off between those, between aseismic slip and the bulk relaxation of the lower crust and upper mantle. In terms of the dynamic modeling, PyLith sort of generally focuses on near source ground motions that's within several fault lengths of the rupture, mainly because one of the strong features of PyLith is its ability to model the dynamic rupture process of the fault itself and the fault friction. And there's been extensive benchmarking with respect to that. So in terms of modeling strong ground motions, looking at the amplitude and spatial variations of ground motions for scenario earthquakes or trying to reproduce past distributions of shaking. Again, looking at coseismic stress changes and fault slip. And this can also include not just the static stress changes, but as well as the dynamic stress changes as a result of the seismic waves. And a lot of the work on sort of rupture dynamics is focused on what sort of fault constitutive models and parameters are consistent with observed rupture propagation that may be seen in a given earthquake and the spatial distribution of those parameters. PyLith has also been applied to volcanic deformation problems. These are often related to inflation of a magma chamber as well as dike intrusion, so modeling the deformation associated with imposing essentially pressure changes in a volume and seeing what the surrounding deformation is. This diagram gives you an overview of where PyLith fits into the overall flow of a typical research problem. So starting on the left-hand side, one needs to start with some model of the geologic structure. Two commercial programs that do that are GoCAD and Earth Vision. Sometimes you can sort of take a given geologic structure, and then you may start with sort of the second step of the process, which is mesh generation. PyLith is tightly integrated into Qubit and Trellis. Qubit is the version that comes out of Sandia National Labs, and Trellis is the academic and non-federal agency version of that same software. It has a very nice graphical user interface and has a somewhat steep learning curve, but we have a lot of examples and there's a lot of sort of help documentation that helps people get going. LeGrit is the Los Alamos Grid toolkit. We use that early on in our PyLith development, but its development was sort of stagnated and didn't have a graphical user interface. So although we still support importing meshes from LeGrit, we don't actively use it anymore. Two alternative codes are TetGen and Gmesh. We are hoping to have some tighter integration with Gmesh in the future, primarily because it is open source and freely available. Whereas Qubit and Trellis used to have a very modest expense about 10 years ago, and the price has gradually ramped up, especially as they commercialized it with the Trellis release. In terms of the physics code, PyLith sits here, takes in the mesh, runs the simulation, and generates files for visualization. Relax is another CIG code that handles sort of more simple elastic and viscoelastic structure. GeoFest is a code developed through JPL. It is freely available. I am not aware that it is under development anymore. Abacus is a commercial code that's sort of a major fine element code used in a lot of engineering applications. And it has a lot of the same capabilities of PyLith in terms of that people can write their own modules to do various things, and it's extensively used for elasticity calculations, and various groups have used it to do some simple dynamic rupture and complex, say, elastoplasticity calculations. On the visualization side, PyLith outputs VTK and HDF5 files that are easily ingested into ParaView and Visit. We primarily use ParaView because it has such a simple graphical user interface. Our HDF5 files can be accessed via other packages that use that can read HDF5. MATLAB has capabilities for reading HDF5 files, so it makes it easy to do post-processing. As PyLith developers, we tend to use matplotlib, which is essentially a Python version of a lot of the plotting that's available on MATLAB. And there's also a Python interface to HDF5 that makes plotting very easy. And so we do most of our post-processing with Python. Relax outputs to GMT as well as VTK files for those applications. So PyLith focuses on the elasticity equation in the current version. So I've written here in equation 1 the elasticity equation in index notation. So the divergence of the stress plus the body force is equal to the density times acceleration in the volume. We have Neumann boundary conditions on various boundaries. We have specified displacements, and then we also may have a specified differential displacement or fault slip that undergoes a rotation, so arbitrary oriented faults on the fault surface. Using the finite element method, we take our strong form governing equation, multiply it by our trial function, and then we want to force the integral of that to be 0 over our volume. After some algebra and applying the divergence theorem, we have it separated into integrals. So we have our stress times the gradient in the trial function. We also have our traction boundary conditions, so integration of tractions over the boundary, integration of the body forces over the volume, as well as the integration of the acceleration times the density over the volume. So this becomes our weak form that we solve. And in terms of discretizing the mesh, we use the finite elements as I mentioned, and so we break whatever volume we have up in 2D triangles or quadrilaterals. In 3D, it's tetrahedra or hexahedra. And many people may be familiar with sort of a bottom discretization here where I have 2 triangles. I've labeled them 0 and 1. So those are our cells in the finite element mesh. And then there are vertices 2, 3, 4, and 5, and I've shown them here. This is sort of what we call sort of an optimized representation of the topology of a finite element mesh, where we have just vertices and cells. For a quadrilateral, we have the same thing. So in this case, I have 6 vertices and 2 cells. But this becomes difficult to sort of do a lot of topological operations in terms of when you want to look at fault surfaces and so forth. And so starting in PyLith 2.0, we now use a intermediate representation where we have cells in 2D we have vertices, edges, and cells, where our cells are surface elements. In 3D we have vertices, edges, faces, and cells. And so in this case we have our 2 cells, 0 and 1, and then each cell is made up of 3 edges, in this case 2, 3, and 4 for cell 0, and 4, 5, and 6 for cell 1. And then each edge has 2 vertices associated with it. So edge 2 is 7 and 8. Edge 3 is 7 and 9. And edge 4 is 8 and 9, and so on. In a quadrilateral, we have sort of the same type of thing, lots of edges, lots of vertices. And we have found that once you start to get to 3D and higher, you have the additional layer. It increases the size of your sort of bookkeeping for the mesh itself, but that's generally only a small fraction of the total sort of necessary memory used by PyLith. So it's relatively small, and it makes sort of the code simpler in terms of doing a lot of complex operations associated with the topology. And I'll get to that in terms of what we do for the faults towards the middle section of my talk today. Getting back to sort of the overall workflow, as I mentioned, PyLith needs a mesh generation input from a mesh generator. So the first step is generating that mesh from Qubit. We read the Exodus file, which is a netcdf file that is exported from Qubit. It contains all the mesh information as well as marking of the boundaries and so forth. From the grit, there is a GMV file which contains the cells and the vertices, and then the boundaries are marked in a separate file called pset file. And we also support a very simple ASCII mesh file format that we use in constructing a lot of our very simple test problems. And so if you can If you can sort of draw the mesh on paper, then we'll tend to use the text editor, but for anything more complicated than that, generally we're using Qubit. In addition to the mesh itself, we need the simulation parameters. We generate those in a conventional text editor. There is both a parameter file that we call a .cfg file, and I'll show an example of what those look like in a minute. And then we also have what we call spatial databases. So these are files that can vary from being very, very simple to being quite complex. And anytime we have a spatial variation in the parameters, we use a spatial database. So these can be as simple as a few points that give a linear variation of some, say, function as a function of depth, say density as a function of depth, or they can be very complicated, such as 3D seismic velocity models. And by abstracting sort of the complexity of that spatial variation into a separate, essentially module that we call spatial databases, it makes our parameter files relatively simple because we can just say what type of spatial database it is and what its file name is, and any other parameters. And by separating out the spatial variation, we do that independent of the mesh. And so it gives us a common interface to be able to query for any spatial variation in the parameters. So essentially, given a mesh file, parameter file, and spatial databases, that's all of the input for PyLith. PyLith then spits out either V2K files, which are ASCII files, or HDF5 files. The HDF5 are binary files that are quite portable and accessible, as I mentioned before, from MATLAB, Python, or anything else that reads the HDF5, has access to the HDF5 library. And we can also write the HDF5 files in parallel. So when we do our large simulations, we use the HDF5 files with the binary output, which are about 10 times faster for output than the ASCII files. And then, as mentioned before, we visualize with either pair view or visit. PyLith is put together as is most easily thought of as sort of a hierarchy of components, where we separate the functionality into discrete modules. And if we have multiple ways of implementing something, then we have a different, what we call, component for each of those alternative implementations. And basically, we can plug and play various components together to form all of the components necessary for a PyLith simulation. And for each component, the top-level code that basically interacts with the user is written in Python. This allows us to very easily and in a sophisticated manner collect all of the user input and do that at runtime. And then we use a library called Swig to basically act as the interface between our C++, which is where we do all of our computation, and the Python, the very high-level code that interacts with the user. One advantage for doing this is we use a Python framework called Pyre that allows us to provide support for units, which allows us to non-dimensionalize everything and work with over a very broad range of scales. PyLith has been used to model things as small as laboratory samples of fault rupture, as well as sort of the 1,000-kilometer length scale of the Earth itself. And other sophisticated things with Pyre is allows us to control the output, how much is shown to the screen. And then also it allows us to dynamically add modules at runtime. So you can potentially add new functionality without modifying the original code itself. This is an example of a parameter file, and at the top is the syntax. So in square braces, we basically provide the component name walking down the hierarchy. And I'll show an example of this hierarchy in a moment. So everything begins with PyLith app, that's our application. And then you walk down, if you go down one level in the hierarchy, you give it the name of the component, the name of the subcomponent, and so forth. And then each component, you can assign a value. You just say the name of the component equals the value. And same thing with parameters. And then everything in orange is a comment. And So here I show some examples for setting the parameters for the mesh generator. So here I'm switching from the default, which is the ASCII mesh, to the qubit reader. So I just say the name of the component is my application mesh generator, and I'm assigning that the reader is of type PyLith mesh.io qubit. Its file name is mesh_quad4.exo, and I'm giving in the spatial dimension of the coordinate system associated with that mesh. The default is 2D, the default is 3D, and so I need to, well, in this case, I'm doing a 2D problem, so I need to switch the coordinate system to have a spatial dimension of 2. Similarly for output, now I walk down the application, the problem, the solution output, and I may have multiple types of output. And so here I'm saying one of those outputs I'm going to create with the HDF5 writer, and I'm going to set the file name. In this case, I'm doing some sort of axial displacement problem, so I just said axial disc.h5. Things like boundary conditions here at the top level, I can create an array of any number of boundary conditions. So this very flexible format allows me to both specify an arbitrary number of boundary conditions as well as then give names to those boundary conditions. So here I have a boundary condition on the x negative, x positive, and y negative faces of my problem. And so I call them x negative, x positive, and y negative. And then I set what kind of boundary condition they are. And then down below, I set the parameters for those boundary conditions. So I can say I can specify which degrees of freedom are constrained, which node set in qubit is associated with that boundary, and then the parameters. So in this case, I'm specifying the type of spatial database. And those of you who are familiar with PyLith may not understand why this is auxiliary fields, but this is actually related to our upcoming version of PyLith, where we've sort of simplified the user interface as well as changed some of the interface of how it comes together. But this gives you an idea of how simple it is to set the parameters for PyLith. One thing you'll notice is that we have this complex hierarchy. It may be sometimes difficult to sort of see how everything fits together. And so what we've done with our latest release is we have developed what we call the PyLith parameter viewer. And so now I'm going to switch out of Adobe and switch over here. Lorraine, can you still see my screen? Should see Chrome on the screen. Okay.
Yes, we're good, Brad.
So this is just with about 3 lines of a Python script that we've included in our distribution. It starts up a web server locally on your machine, and it tells you to go to this web address. This is just the local address, and so I can choose a file now that is written out by PyLith. It's written in a JSON format. And so what I'll do is I'll collapse everything here. It shows the timestamp when the file was written, so that lets you know, whether you're using the latest version or not. If you change the version or you generate the file again, you can simply hit the reload button. If you click on the version tab, you have a complete listing of the version of PyLith that was being used. It also tells you on what type of machine you are running when you ran PyLith. So in this case, I am using a Git version. It gives everything all the way down to the Git revision, Git hash when it was configured. It tells me the version of all the dependencies, such as PETSI, MPI, the spatial data, proj, HDF5, NetCDF, and as well as all of the version of Python and what modules and where they were found. So getting back to the parameters, if I collapse everything, you'll notice at the top level I have an application. Then I have an MPI launcher, which if I click on the red text over on the right, it shows me all of the parameters for that launching that MPI job. The mesh generator here you'll see is if I walk down another hierarchy, there's a distributor, refiner, and the reader. So the reader is what's reading the mesh. I can see whether it's the properties, that's sort of low level, provides the descriptions, where it's set from. And so in this case, here is the name of my Exodus file. The description is the name of the qubit Exodus files, and it tells me exactly where it was getting this from. So I specified this in my PyLith app.cfg file on line 40. And if I walk down to my problem, I can click on the problem, and let's look at boundary conditions. So in this case, I have a Z negative, X positive, X negative boundary condition. And if I click on the X positive, I'm constraining degrees of freedom 0 and 1, that's X and Y. My node set is going to be face X positive. You can see that in this case, I specified that in a different .cfg file. And then I had a number of spatial databases. So we think that this new parameter viewer will provide a lot easier accessibility to all of the parameters and how they fit together in PyLith. It also provides sort of additional documentation that's much easier to look at and examine than previously when we just generated a big text file that was sort of had the indentation corresponding to the hierarchy, but didn't really allow you to really understand the hierarchy and browse through it. So PyLith users and new users, we would welcome people experimenting with the parameter viewer. And ultimately, we'd like to be able to specify parameters, but that's a significant, given the dynamic capabilities of PyLith in terms of its configuration, that's quite a difficult problem to set up the user interface to specify the parameters using the GUI interface. So right now, it's limited to just viewing the parameters. So let's go back to the slides. I'll continue on. Give a little more information about our spatial databases. So some examples are, if we have just a uniform value for a Dirichlet boundary condition, we would call that a zero-dimension spatial database. If you have a piecewise linear variation of tractions for a normal boundary condition, we would associate basically that piecewise linear variation with a 1D variation. Things like a complex 3D seismic velocity model that has a 3D variation in the parameters. And as I mentioned earlier, it's generally independent of the discretization of the problem. So you can specify, once you're given your problem, your spatial databases, and then you can play around with your mesh in terms of different discretization resolutions or cell types, and your spatial databases won't change. The available spatial databases in PyLith, we have a uniform database that's optimized for uniform values. So if you have, let's say, a uniform displacement on a boundary condition, you can write there in the .cfg file, write out in 3 lines what that spatial database, what its values are, and where the points are. And so that makes it very simple if you have just a uniform value. And it's obviously very fast because you're specifying the value right there in the code. If you have some sort of more arbitrary distribution of points, so say like a linear variation of density with depth, then you can use a simple database. This is for arbitrary distributed points in space, that if it's just a single point, then it's essentially a uniform distribution. But if you have a 1D variation, you can either make a 1D variation with depth, you can make it 1D along some line at the surface, you can make it 1D at an angle, like down the fault dip, and so forth. 2D variations, if you have a 2D variation of slip, you can either specify that as sort of a cross-section or even the map view of the slip. But as long as you remember that things are going to be distorted when you map onto a dipping fault plane. A simple grid database is when the points are in a logical grid, so they don't have to be evenly spaced. They can be unevenly spaced, but if they're in a logically rectangular grid in whatever coordinate system you want, then you can. It provides a much faster interpolation rather than having an arbitrary cloud of points where we have to figure out where our point of interest is in that space. and do the interpolation. Our current interface to the SCEC CVM-H seismic velocity model is relatively old. It's back in version 5.3. We do have plans to update that in the future. And the other spatial database that I want to mention is the zero displacement database. And that's basically a special case of a uniform database with zero values for the displacement. So instead of having constantly specify fixed boundaries, you can just specify a zero displacement database. Also, sort of moving back to discuss a little more about the PyLith design and the features. PyLith leverages a number of packages developed by computational scientists. So the main one is PETSI, which is shown here in the green. PETSI handles all of our finite element data structures. It also handles all of our parallel objects for linear algebra, so matrices, sparse matrices, vectors, distribution of the mesh. It is developed by Aagaard National Laboratory, and Matt Nepley, the computational scientist associated with PyLith development, is heavily involved with PETSI. PETSI has interfaces to HDF5 itself. PyLith also has a direct interface to HDF5. PyLith reads qubit files from netcdf. As I mentioned before, we have our spatial database library. It relies on a projection library called proj.4. We have our Python framework for gathering user input. That's Pyre. Spatial database files can also be interfacing with NumPy, so that's another dependency. And then we have low-level the message passing interface for parallelization, and then PETSI for matrix vector operations interfaces with BLAS and LAPACK. The good news is, even though we have all these dependencies, we distribute binaries where we bundle all this together. And for if you need to build on the cluster, we have an installer that will build PyLith as well as all the dependencies that are necessary as well. That has greatly improved the installation process. In our PyLith development, we follow the CIG best practices. And some of the best practices that I mentioned, I would like to mention are for version control. We create new features in separate branches that allows us to simultaneously add new features independently. So some features can be added very quickly. And then some features that may take longer can be simultaneously worked on. And then they get merged to a master branch, which is our stable development branch. And so our master branch is almost always stable and contains the latest features that have been well tested. In terms of the coding and how we've styled it, we've attempted with our .cfg files and spatial databases to create a user-friendly specification of the parameters at runtime. None of the parameters are hardwired into the code, so you never have to recompile if you change parameters. We have a development plan that's updated annually and sometimes even more frequently than annually. There are a variety of templates where we show how users can add features or alternative implementations, such as different bulk rheologies, different friction models, without modifying any of the PyLith code itself. PyLith is quite portable. The build procedure is independent of compilers and optimization flags, and you can create multiple builds from the same source installed into different directories. So we often do this where we have a debugging version and then a highly optimized version built from the same source on our machines. We have an extensive example suite with varying levels of complexity. So we sort of build up from very simple problems, slowly adding more sophisticated features and sort of boundary conditions and fault implementations and so forth to sort of walk the user from running very simple problems to sort of more complex problems. As I mentioned before, changing the simulation parameters does not require rebuilding. And in the version, I think it's 2.4, we added display of version information via the command line argument, so you can always tell exactly what version you're using. And it also will spit out how to cite PyLith for that particular version. With the latest version, this whenever you run PyLith, it saves automatically. By default, it'll write out that parameter file that gives you the version information as well as all the parameters. We do not have sort of using that file as input for complete reproducibility, but that's the direction we're heading. So that it'd be very easy to reproduce exactly what you ran before simply by using that JSON file as your input file. That's coming soon. We use GitHub extensively for our code repository. We document our code in the style of Doxygen. We use CPP unit for unit testing of all our functions. And we have integration testing primarily with the Travis continuous integration that is hooked up directly to GitHub. And then we looked at how well much of our code is currently being tested with test coverage tools provided by GPyth. In addition to sort of the unit tests, which are sort of testing at the single function and multiple function level, we have serial and parallel pass-fail tests of full problems. Most of these are sort of simple problems, and we're working towards integration with the method of manufactured solutions to create even tests for a broader range of problems. And then we have serial and parallel full benchmark tests. And primarily those are done at sort of the code comparison level, such as those done by the STIC dynamic rupture benchmarking. So I'll now briefly go over the sort of the full list of current features that are available in our version. Sorry, when I mentioned version 2.4, that was 2.1.4. Our current version is 2.2 that was released at the end of March. And so the features available in that release are, we have time integration schemes for quasi-static problems as well as dynamic problems for both infinitesimal and small strain formulations. Our bulk constitutive models include the elastic model, linear elastic, viscoelastic models, a generalized Maxwell model with 3 Maxwell models in parallel, a power law viscoelastic model, a Drucker-Prager elastoplastic model. For boundary and fault interface conditions, we have time-dependent Dirichlet, that's prescribed displacement boundary conditions, Neumann or traction boundary conditions, as well as point forces. We also, for dynamic problems, we have absorbing boundary conditions. On the fault, we have both prescribed slip and frictional fault interface boundary conditions. When prescribing the slip, you can put in multiple ruptures occurring at different times with their own progression of slip. Our fault interfaces, we can have T intersections, and as well as gravitational body forces in the bulk. Our fault constitutive models include static friction, linear slip weakening, linear time weakening, as well as Dietrich-Carina rate and state friction with the aging law. Other more general features are automatic and user-controlled time stepping, ability to specify an initial reference stress and strain state, as I mentioned, output via VTK and HDF5, and the user can select to output the solution over the volume as a function of time, solution over or at any number of specified time steps. So say every X number of years or every N time steps, say skipping 3 or 4 or just at the end. Solution over a surface boundary. Generally, this is used to get the solution at the ground surface because that's where most of our observations are. We also have the ability to have the solution interpolated to user-specified points with station names. So that's primarily for GPS and seismic data where we have a known location of, say, a GPS sensor or a seismic instrument. We also have output of the state variables for each material. This would be generally stress and strain. For the viscoelastic models, you can get the viscous stress as well. Elastoplastic models, plastic strain. The fault information, we have the slip and the tractions, as well as slip rate. And some of the final list of features as I mentioned before, automatic conversion of all units for the parameters. We also have the ability to do parallel uniform global refinement, so you can generate your mesh at, say, 1/2 or 1/4 of the final resolution you want in your simulation. When running in parallel on a cluster, it'll distribute the mesh and then refine everything on each process globally by a factor of 2 or 4. And that allows you to run a much higher resolution while generating a coarser mesh. We have, by interfacing with PETSA, we have access to all their linear and nonlinear solvers, and we have, within this framework, developed a custom preconditioner with an algebraic multi-grid solver that is generally our preferred solution scheme for quasi-static problems that gives very good scaling in parallel. And I believe in version 2.1, we added the ability to output the simulation progress in terms of, like, every 5% of the simulation, it'll output how far it's gotten and when it expects to be done. So if you're running a large number of time steps after 5% of the runtime, it'll give you an estimate based on how much time it took per time step of when it expects to finish. And that's useful to know whether your simulation is expected to finish in an hour or several hours. Before I give an overview of the parameters or the new features in PyLith 3, I just wanted to mention our fault implementation. These details are given in a paper that was published in 2013 that I'll show in a couple slides here. But generally what we do is we take our fault interface, we have the tractions that are coupled on the two sides, and so what we do is we provide a normal to this fault interface, and we refer to the side that to which the direction of the normal points is the positive side, and then the opposite side is the negative side. And we have equal and opposite tractions as well as displacements on the two sides. Now, within as a user, to use a fault surface in your original mesh, basically you create a mesh, and then where you want the fault surface, you need to make sure that you have a set of faces or edges along that fault surface. Here I've shown that in blue. Generally, this means you create that fault surface within the mesh as an interior surface within your volume. And all you have to do is mark the nodes that make up that fault surface, as well as any nodes on the buried edges. And then as part of the PyLith simulation, we will separate the faults, and then we will add nodes and cells accordingly. And so this process is shown here on the right. And so what we end up with is we have inserted these 0 volume or 0 area cells in between the two sides of the fault. And we encapsulate our entire fault implementation using these 0 volume or 0 area cells. And so as a user, basically all you have to worry about is defining the geometry of your fault surface and marking it, and PyLith will handle the complex topological operations necessary for creating that fault surface. And then in terms of the implementation, much like a Neumann or traction boundary condition on an exterior surface, we have a traction boundary condition on our interior surface. In this case, it involves Lagrange multipliers that I've shown here as L. These are Lagrange multipliers are vectors that correspond to the tractions on the fault surface are equal and opposite on the two sides. So that's why on the negative side of the fault I have a plus sign. On the positive side of the fault I have a negative sign. And then in my constraint equation, when I want to specify the slip, I have the slip minus of this displacement is equal to 0. And when I put all of this together, we end up, if our original system without the fault was a matrix times the displacement equals sort of our forces, we combine that with our constraint equation, and we end up with this equation here, where I have my original full matrix, a small matrix C that's related to the orientation of the fault surface, displacements, Lagrange multipliers, my normal right-hand side, and then slip. So you can see that I have the coupling of the two sides of the fault through the Lagrange multipliers. When I specify the slip, basically I'm specifying D on the right-hand side, and I will solve for what tractions are required to generate that slip. And then in spontaneous or dynamic rupture, I am adjusting the Lagrange multipliers according to the friction model to generate the slip that is consistent with those friction values. The advantage of this approach is that the fault implementation is completely local to the cohesive cell. The solution includes the tractions generating the slip, the Lagrange multipliers. We retain the block structure of our original matrix, including symmetry. And the offsets in the mesh mimic the slip on natural fault. So I have sometimes people will try and put in a sort of finite width fault zone that's where that width is very artificial and dependent on the numerical implementation. Whereas in this case, we have literally a dislocation in our finite element mesh. Some of the complexities of this approach is the cohesive cells require adjusting the topology of the finite element mesh. That burden is on us as PyLith developers to implement that. And then the scaling of the preconditioner and solver is a bit more complex because we have a zero on the diagonal of our matrix when we do quasi-statics. So I want to spend about the last 10 minutes here going over new versions in PyLith 3 and the direction that PyLith development is going. And in version 3.0, we're really focusing on the multiphysics approach as well as higher order spatial and temporal discretizations. And along with that will come adaptive time stepping using PETSI time stepping algorithms. And we have developed sort of the background theoretical work to improve our spontaneous rupture simulation, but we don't think that'll make it into our version 3.0 due to time constraints. And we're expecting to release version 3.0 by our June workshop. So to give you an idea of how we're doing multiphysics, basically in equation 7, I show that if we have our strong form of PDE, we multiply by a trial function with the finite element method and set that equal to 0. And the goal here is to minimize the error with respect to unknown coefficients. And this leads to a very general form of our PDE in most cases, or at least in cases of the governing equations that we want to solve, where we have some function times our trial function, plus another function times the gradient in the trial function. And as I go forward, with PETSI time stepping, PETSI solvers want our governing equation in the form of f of t s or s dot is equal to g t of s with some specified initial solutions at some time. And so in using the finite element method, we break the f on the left-hand side into our f times the trial function and f outer product with the gradient in the trial function, and then the same thing with our right-hand side. And so what we do is basically we create these kernels F0 and F1, and the application code will handle all of handling the gradient and the products associated with those functions. So the PETSI TS for explicit time stepping requires that the left-hand side be equal to S dot. Normally we have an inertial term multiplied by S dot. And so what we do in terms of setting up our governing equations is we basically create a fake right-hand side that is the inverse of our inertial term times our normal G. So we basically we give PETSI the G star, which is our inverse of our mass matrix times our original G. And so that gives us S dot on the left-hand side, and we can proceed with the normal interface for the time stepping. I think I'll skip this slide and show an example of how we do this for the elasticity equation. So here we have our S dot term. So in this case, it's the second derivative of the displacement times density. We have our body force, and then we have the stress on the right-hand side. Again, our normal traction boundary conditions. And when if we remove inertia, so if we just do implicit time stepping for our quasi-static problem, then our displacement field our unknown is just equal to the displacement field, and our left-hand side is 0. So this F0 function is 0. We don't have an F1. And our right-hand side, we have our body forces becomes our G0 function. It's multiplied by our trial function. Minus the stress tensor is our G1 function. It gets contracted in with the gradient in our trial function. And then our boundary condition also has a similar form in that we have a G0 function with our traction that's dotted in with our trial function. And so what you can see is that all of the complexities associated with our governing equation are shown in these little kernel functions F0, G0, and G1. And the way we're reformulating this in terms of PyLith and the governing equations is that our governing equations and materials are encapsulated in these fine element kernels. They get specified at the application level, and PEPSI handles doing all of these integrals and products of contraction of the kernels with the trial functions and the fine element basis functions. And in this case, for elasticity, all of the different constitutive models are encapsulated in providing different functions for G1. For explicit time stepping, on the left-hand side, we set our solution equal to composed of both the displacement and velocity fields. So in this case, we have two functions, two equations. The first one is that the derivative of the displacement is equal to velocity. So that's a very simple equation. Notice I have S dot here on the left-hand side. And my right-hand side kernel is simply just the velocity. Then I have, instead of acceleration, I have the time derivative of the velocity on the left-hand side. So that's my v dot function. In the right-hand function, I have sort of my inverse of the mass matrix that I mentioned before. Plus, I have my original kernel functions that I had in the quasi-static time stepping. So you'll see here that with just some very small variation in these kernels, I can switch between the implicit and explicit time stepping set up within PEPSI. So you can see a lot of reuse of code here in terms of what these kernel functions are across the governing equation, as well as just changing how my stress is calculated. That changes what constitutive model I'm using. So here's just a very simple comparison between the implicit and explicit time stepping and the kernels involved. And so you can see, I have a few more kernels for explicit time stepping compared to implicit time stepping. But in all cases, there's very simple kernels for these are for the residual and for the Jacobians and implicit time stepping. They're also quite simple functions. So I'll just spend 1 minute going over the pore elasticity. Now I have multiple governing equations, primarily the one for the fluid as well as for the solid. And so equation 21 is basically reproducing the quasi-static elasticity equation. And then I bring also in for pore elasticity the mass balance of the fluid. So I now have an additional governing equation that couples the pore fluid pressure with the elastic deformation. I bring in additional governing sort of supporting equations that relate these two, such as Darcy's law, the constitutive behavior of the fluid, and the constitutive behavior of the solid. And this gives me this set of equations. So now I have two sets of governing equations. So I have multiple sets of these same kernels that couple the two sides, or couple the displacements and the pore fluid pressure. So you'll notice from my elasticity, it's relatively the same, except now my G1 function is a function of both the displacements and the pore fluid pressure. And then, excuse me, for the fluid equation, I have things like the fluid flow, the gradient of the fluid flow, things happening on the boundaries. And so you see that the pore elasticity involves many of the same kernels as elasticity plus a few additional ones. And this is how we're implementing the multiphysics, basically through these additional kernels that couple additional solution fields. So in our current version of PyLith, we have just the displacement field, but we're moving towards, in version 3, being able to specify multiple solution fields such as displacement, displacement velocity, displacement and fluid pressure, displacement, perhaps displacement temperature and fluid pressure, and so forth. For sake of time, we'll skip over that discretization. So to summarize our multiphysics implementation, we've gone this route of creating these pointwise kernels that look a lot like the partial differential equation. That gives us tremendous flexibility in that we can pose the problem in any spatial dimension with arbitrary numbers of physical fields, so the code is very flexible. Looping over the cells is all handled by and the different cell types, such as a triangular cell versus a quadrilateral cell, is all handled within PETSI and the internals of PyLith, and providing sort of optimized implementations for various hardware architectures. That can be all done at the library level, and it's generally only one or a very, very small number of functions that actually have to be optimized for things like running on GPUs or these multi-core processes and hardware that are coming out where you have lots of cores on a single node. And a new discretization scheme can be enabled in a single place of the code. So very extensible, very easy to, it can be optimized with very limited interaction with the code. And the efficiency is both in terms of maintenance, in that only the single routine needs to be optimized. And as an application scientist, I only have to write my implementation once. And then sort of porting to different architectures is handled on the computational science side. So to wrap up, to get PyLith, we have binaries for desktops and laptops for both Mac OS X and Linux, both 64-bit and 32-bit versions. For Macs, we generally support the operating systems that are supported by Apple. So currently that's, I believe, 10.10 and later. For Linux, we generally support everything, all of the implementations that are under support by Ubuntu. So we build on Ubuntu 12.04 right now, and so essentially any Linux distribution, 64-bit or 32-bit, that is currently maintained should be supported. If you're running on a cluster, you generally need to build from source because we need to interact with whatever open MPI library is provided by your cluster, and that's hardware specific. But we do have this installer that builds PyLith and all of its dependencies from source. We recommend that a system administrator do that. We also have an alternative instead of our binaries, which is a Docker container. And this is what we currently recommend for any Windows users. Our Docker container runs on any system where you've installed Docker. And so this is basically a slimmed down virtual machine. It has a minimal, our container contains a minimal version of the Debian Linux operating system that includes the compilers, all of the sort of system libraries, as well as PyLith and all the dependencies. And then we also add in, to sort of give you a full self-contained system, Python module for 2D and 3D plotting, a simple text editor, as well as the Firefox version of the GNU version of the Firefox web browser, so you can view the PyLith parameters. We have a number of resources available for PyLith users. We have our upcoming workshop, June 26th through 30th. We have a web page where you can get the binaries, the installer, the link to the Docker image, as well as the user manual. We have a wiki that shows our development plans, as well as contains slides and videos from past tutorials. You can see publications using PyLith by visiting the Geodynamics reference-based library. We have a mailing list that we use to respond to PyLith questions, and then all of the source code is available directly from GitHub or the PyLith download page. So I'll wrap up there. I guess I went a little long, but I'm happy to take any questions that people have.
Thank you very much, Brad, for that very informative webinar. If you have any questions for Brad, please go ahead and type them into the chat window or raise your hand, and I will see if I can open your mic. One question I have, Brad, is with the additional computation of additional kernels, what do you estimate the additional resources that someone's going to need to run the multiphysics?
Well, the more fields you bring in, sort of increases the size of the sparse matrix that is stored. So if you have both a displacement and a fluid pressure field, obviously displacement in a 3D problem has 3 vector components, whereas fluid pressure is a scalar. So in that case, it's on the order of, say, 1/3 more memory. With the coupling, it's probably a little more than that. So, you know, it will take a little more in terms of memory once you start to bring in the multiphysics capabilities. You know, generally, you can just use, in some sense, the solution is to use either a bigger desktop machine or use more processes on the cluster. And I would say to the most extent, people's machines are probably growing as fast as our memory use in PyLith or faster. So if you could run a problem, say, a few years ago on your desktop, if you have a more recent desktop, you can probably still run about that same size problem with multiphysics.
And what about the convergence rates?
We have not really looked at that yet, but that's one area where all of the sort of different preconditioners available within PETSI will allow us to develop some very good preconditioners for the types of problems that we expect to solve. So in some sense, the precondition we use for elasticity will still work very well for the elasticity portion, and so it's then just bringing in the types of preconditioners that are needed for the fluid pressure.
Okay, so Renee has a question for you. He thanks you for the talk and asks, can you guarantee that the multiphysics kernels provided by the users do not change the structure of your system matrix and deteriorate solver performance? I guess well, Lorraine kind of asked the same thing.
So basically, when we set up our sparse matrix, it is set up based on the kernels. So if the kernels are coupling the displacement and the fluid, or based on whether I have an F0 or an F1, or in the Jacobian, there's actually 4 functions, G0, G1, G2, G3. We can look at what kernel are specified for that particular physics and set up the sparse matrix accordingly. So it's really actually creating the sparse matrix to match the physics. Now, in terms of degrading solver performance, it's relative to what? Relative to elasticity? Well, yes, it may not be as good as elasticity, but that's really not a fair comparison because the physics are different.
It sounds like you can kind of tune the matrices a little bit as well with different kernels. Renee says thanks. Any other questions? I think Brad mentioned that he hoped to have version 3.0 out by the workshop, and that workshop again is in June 26th to 30th in Golden, Colorado. And if you're interested, of course, in getting more hands-on experience with PyLith and, of course, working with the developers and the rest of the community, please go out to geodynamics.org and apply to attend the event. It's filling up fast, so if you're interested, please go out and sign up. So this webinar actually wraps up this year's seminar series. We thank everybody for joining us this year, and we look forward to seeing you again in the fall. Thanks a lot. And thank you again, Brad.
You're welcome. And if anyone else has any additional questions, don't hesitate to send email to cid-short@geodynamics.org, and we can answer your questions via email.
Great. Thank you once again. Bye, everybody.